Hello again. Let us conclude our introduction to organic chemistry by today looking at organic reactions and mechanisms. For our lesson objective, we're going to describe homolytic and heterolytic fission, understand how to draw reaction mechanisms for both, and identify a number of characteristic organic reactions. The learning outcomes, as always, that we're addressing from the Cambridge curriculum just below there. So we have introduced a multitude of different new concepts related to organic chemistry. We're going to finish off our introduction by introducing some characteristic reactions and also the idea of drawing reaction mechanisms. And with these three lessons, we've got the fundamentals we need to then look more in depth at the individual homologous series and the reactions and properties that they have. So mechanisms are incredibly useful. We can show a very large amount of information very succinctly when we combine our things like our skeletal formulas with these things that we're looking at called reaction mechanisms. So we can use reaction mechanisms to summarize chemical reactions in a series of steps, and this can contain a lot of information and present that very succinctly and very quickly. What they do, they use these curly arrows to track the movements of electrons. They show which covalent bonds are broken and which covalent bonds are formed at each step, because that's all a chemical reaction really is. We have the conservation of mass, the matter that we start with, the atoms that we start with need to be the same that we end with. All we do when we react to something is we just rearrange how they are bonded to each other. So in our organic reactions, these mechanisms are very useful because, like I said, it's very easy to show exactly what bond is being broken, what bond is being formed between which atoms, and I suppose even why that is occurring. So here's an example of what they look at using these curly arrows. We can show the electrons where the bonds are being formed. We can show where the bonds are being broken. This is obviously above anything we would need to look at, really, but it's just a good example to show off to begin with. And it also shows the formation of any intermediates or any transition states. So it shows stepwise, potentially, what could be occurring to get from the start to get to the end. So it uses curly arrows that show where the electrons are originating from and to which atom they are forming a bond to. And you need to include the following information when we are drawing reaction mechanisms. We need to show any charges on any atoms, any dipoles, the lone pairs of electrons, and the curly arrows showing these bonds being formed and these bonds being broken. So like we do, let's start nice and simply. Let's look at the two main types of organic reactions that we have. Something called homolytic fission and something called heterolytic fission, where fission means division or splitting into two or more parts. So it's all to do with looking at the breaking of the bonds, the breaking of the covalent bonds more specifically between our non-metal atoms. So let's start with homolytic fission. Like we do with these words, it can be very useful for us to break them down so they don't look so daunting. Homolytic fission we can just break into three parts. Homo being a prefix, ancient Greek meaning the same. Lytic coming from lysis, you might have heard that in something like biology. Lysis means breakdown or decomposition, and then fission, like I just said, means to divide or split into two or more parts. So in homolytic fission, we are breaking down something into two or more parts, and we're doing it for the same in some capacity. So what that same is referring to is the electrons that are leaving the covalent bond when we break it. The bond breaks and each atom leaves with one electron from the pair in the initial covalent bond. So when we're doing our chemical reactions, we are breaking and making covalent bonds, like I said just before. Now we know a covalent bond is a shared pair of electrons between two atoms. So in our homolytic fission, we are breaking that bond, we're doing the fission of that bond, and each atom is taking one electron. Homo meaning the same, as in they're getting the same amount of the electrons in the original bond. So it uses these half arrowheads as opposed to full arrowheads that we might have seen just in this diagram over here. We use full arrows to show an electron pair. We use half arrows to show just individual electrons. And it forms species called free radicals, which are atoms or molecules with a single unpaired electron. And these are very, very reactive species. They don't like existing like this. They will look for anything in the vicinity, in their little chemical vessel that they're in, to try to not be a free radical anymore. So we can use these to make reactions occur, free radical reactions, where something might not be reactive enough to react without it. Let's look at an example of all of this. Here is a general equation where we've got something covalently bonded. This is just showing two atoms, but this could be a part potentially of a larger molecule. So we've got a covalent bond between A and B, and we get the homolytic fission where one of the electrons goes to the A atom, one of the electrons goes to the B atom. The A and the B aren't actual symbols on the periodic table, they're just placeholders for any atom that would be in this specific scenario. So we can see here, they're getting the same amount of electrons, they're getting one electron each from that original covalent bond. Let's look at drawing a mechanism for this. So I will use my general reaction. A, B, so this is our covalent bond. We are forming a free radical for A and a free radical for B. Just showing that lone electron that it's got to get the free radical species. So we can show the electrons going with half arrows like that. So it's saying that the electrons in this original bonded pair, one of them is going to the B, and that's what we show over here. One of them is going to the A, that's what we show over there. We've got conservation of mass. I mean, A over there, B over there, it's a balanced chemical equation. So we use the half arrows to show the homolytic fission, whereas we use full curly arrows, which we'll look at in just a second, for the heterolytic fission, but we're not looking at that right now. Here's a question. Based on what I've just shown you, can you draw a reaction mechanism to show the homolytic fission of HCl? I've even given you the overall reaction. So this time we're actually doing it with actual elements. Can you draw a mechanism to do that? Pause, have a go, and then check with it now. So no tricks here. We're just putting our hydrochloric acid instead of our arbitrary A and B. So we show the homolytic fission like that. One of the electrons goes to make a hydrogen free radical. One of the electrons goes to make a chlorine free radical like that. We're showing the mechanism. We are showing where the electrons are going. We're showing the fission, the breaking of the bond, and the distribution of electrons. So in this case, homolytically. Rightio. Generally, this is the less common mechanism than heterolytic fission. Pretty much all of the reaction mechanisms we look at in this course is examples of heterolytic fission, but there are some examples of homolytic fission that we need to be familiar with. Homolytic fission occurs in free radical substitutions that we will look at quite in depth in a later lesson, but let's just cover it now. We have three general steps in a free radical substitution. The first is the initiation step. Homolytic fission of the covalent bond, high energy of the bond generally requires light or heat. So the initial step is we sever the bond homolytically and we form the free radicals. Initiation, the initial step. Now, we've talked about covalent bonds being strong, so this requires some sort of energy input, usually in the form of UV light or in the form of heat, in order to fission that bond. Then we make these highly reactive free radical species. And what these do is these create a chain reaction where a free radical desperately doesn't want to be a free radical, so it'll cause something else to be a free radical to therefore, get the electrons that it wants back. That will form another free radical, which can form another free radical, so on and so on. And it's this propagation step, which is this chain reaction of free radical formation. Due to the free radical's highly reactive nature, they attack other molecules, causing other free radicals to form in a chain reaction. And then that finally ends in a termination step. It terminates when two free radicals form together, forming a new molecule, and the chain reaction has stopped because we don't have that highly reactive species anymore. So once all of the free radicals terminate, they find other free radicals to form another covalent bond with. The free radical substitution reaction in this case will cease. Quick introduction there. We will see that later on, like I say. So now moving on to the other kind of fission, the heterolytic fission. You might be able to infer, in fact I think I said it before, heterolytic fission, hetero, ancient Greek prefix, we're using it to mean different. So whereas our homolytic fission, they were getting the same electrons when the bond broke, when there was a fission of the bond, they were getting one each. Heterolytic fission, they get a different amount of electrons. So in fact, one atom gets both the electron pair, the other atom gets none. Like I said, this is the much more common reaction mechanism that we observe when we see organic reactions. So hetero, ancient Greek for other, lytic, again meaning license, and then fission, lysis, and then fission, again meaning division. So the initial covalent bond breaks and one atom takes both the electron pair in an uneven distribution. So we use full arrowheads as opposed to the half arrowheads. Half arrowhead, half an arrow for one electron, full arrow for 2 electrons. Rightio, let's have a look at an example. Now the more electronegative atom will take the electron pair. Why? Well, we've got to consider what electronegativity is. Electronegativity is the ability for an atom in a covalent bond to attract an electron pair closer to itself. So it makes sense that the electron, the atom that has the electron pair closer to itself is going to be the one that is going to take the electrons as opposed to the less electronegative one. So unlike the homolytic fission and heterolytic fission, when one atom gets the electron pair, it will form ions as opposed to radicals. So the one that gets the electron pair will form the anion. The one that loses the electron pair, now being electron deficient, forms the cation. So if I draw a mechanism similarly to how I did just before in our heterolytic fission, we've got our A and B. Again, A and B are just saying general atoms. That's not any atoms that actually have A and B as their symbol. So we form a ion using a double arrow because it's heterolytic fission. Double arrowhead means it's taking both electron pairs. So we form a cation for the A and a anion for the B. The more electronegative one taking the electrons with it. Rightio, let's do the same reaction that we did before, but instead, can you draw a mechanism showing the heterolytic fission of HCl, not the homolytic fission? Pause now. Do that the same way you did before, just 1 or 2 small differences, and check the answer now. It just has the double arrowhead where we've got the HCl, chlorine being more electronegative than the hydrogen. If this heterolytically breaks, fissures, then we're going to get the hydrogen cation and the chloride anion. So we're going to look at characteristic organic reactions. And whether it's doing what kind of fission it does and what kind of reaction it does can be manipulated a lot by the reaction conditions and what you are reacting. Rightio. So in organic chemistry, heterolytic fission can often form these things called carbocation intermediates, which is a carbon with a cation. Pretty straightforward there. Because we have our backbone, our organic molecules all have these carbon structures. When we do heterolytically fission a carbon, when the carbon is the one that is breaking the bond and losing the electrons, we can form these things called carbocations. For example, if I have chloromethane, where we've got CH3Cl, I'll just do a straightforward displayed formula like that. Chlorine is more electronegative than the carbon. So if we fission that heterolytically, then the chlorine is going to form chloride anion, and we form a carbocation intermediate. Carbo because of carbon, cation because of a positive charge. So these are quite common to see when we are doing organic reactions. Now, we can form different kinds of carbocations depending on how many alkyl groups, so depending on the carbon chain attached to our carbocation, we can form different kinds of carbocations. So this has no alkyl groups that are attached to it, so this is just a methyl or a methyl carbocation, whereas if we had one other alkyl group attached to it, so we had an R there and then these are just hydrogens, we would form a primary carbocation. 2 would form a secondary carbocation. 3 would form a tertiary carbocation. So primary for 1, secondary for 2, tertiary for 3 other alkyl groups. Now these stabilities, things with a positive charge tend to not like having a positive charge. They want to be neutral again. So depending on how many other alkyl groups are attached to our carbocation will dictate how stable that carbocation is. And this is all due to something called a positive inductive effect. We'll talk about that in just a second, but we can talk about the trend. If we have a carbocation with more alkyl groups, that's going to be more stable than one with less alkyl groups. And it's all to do with the fact that the other carbons have electron density in their inner shell electrons that they can donate to help stabilize that positive charge. So even though the carbocation, if we had other alkyl groups here, oh, I've got to change the camera. If we had other alkyl groups here, it's still a positive charge, it's still not the most stable thing in the world, but we can donate electron density from these other alkyl groups, whereas the hydrogens are unable to do that. So the more that we can donate electron density into that positive cation, the more we can stabilize that, because positive and negative stabilize each other. So the more alkyl groups we have, the more stable the carbocation will be, and we call this the positive inductive effect. Alkyl groups can donate electron density by pushing electrons away from itself and stabilizing a positive charge. These are called electron donating groups. So that's what I'm saying here. The alkyl groups, our other carbon chains, can donate electron density into that carbocation and help to stabilize it. And the carbocation can then react as an electrophile with a nucleophile. So these are two terms that we're going to hear a lot. An electrophile, again, let's break down the words into its two parts. Electro has something to do with electrons. Nucleophile has something to do with the nucleus. Phile as a suffix means that there's some sort of attraction or affinity for it. So if we have an electrophile, it's a species that has a liking for electrons. So it wants to get some sort of electronness, wants to get a negative charge in some capacity onto it, whereas our nucleophile likes nucleuses, and nucleuses have positive charges. So it's a species that's looking for a positive charge to help, to react with rather. So electrophile is a species that can accept a pair of electrons with a nucleophile, a species that can donate a pair of electrons. Two terms we're going to be hearing of lots and lots in the coming lessons. Lastly today, we're going to finish off this unit by just looking at some characteristic organic reactions that we can use to categorize reactions that are observed when we're doing synthetic organic chemistry. Now, the good news is that the names of a lot of these types of reactions, the general name for it, makes it very clear what's occurring in the reaction. What do I mean by that? Let's have a looky-loo. So the first kind is an addition reaction. An addition reaction is going to add two things together. It's the formation of a single product from the addition of two or more reactants. So here we've got A plus B and we form some sort of C, such as in the bromination of ethene. We've got ethene, bromine, we get two things, we add them together to make one thing. An addition reaction, just like we use the word addition in our everyday lives. An elimination reaction is essentially the opposite of that, I suppose. You're eliminating something. It's the removal of a smaller molecule from a larger one. So we're starting with one thing and we form two things, such as the dehydration of ethanol, where we've got one thing here and we form two things. We can categorize this as an elimination reaction. So this is what I mean by they're general reactions. We can use them to categorize a whole magnitude of different specific chemical reactions. And all these reactions I'm using as examples we're going to look at later on in much more depth. The next kind is a substitution reaction. You might be able to guess what's happening there. We're going to substitute something. It's the replacement of one functional group, whether that's an atom or a group of atoms, by another. So for example, we've got some species AB, react that with some species CD, and we substitute the A with the C. So it becomes AC, and we substitute B and D together. Swapping over, substituting. Again, just using these words how we would in our everyday vocab. Here's an example, substitution reaction with an aqueous alkali. We got bromoethane, sodium hydroxide, and we substitute the bromine for a hydroxyl when we go from a halogenoalkane to an alcohol. Next kind is a hydrolysis. So let's break this down. Hydro, something to do with water. Lysis, to do with breaking down something. Breaking down a molecule with water, often sped up by an acid or alkali. So we get our molecule here, AB, and we react it with our water, H2O, and we break that down into something else. An example, hydrolysis of the ester methyl ethanoate. So we've got a molecule here, we react it with water, and we break it down into two other things. Now the last two are things that we've looked at before, but we use these words in a slightly different context in organic chemistry, and they are oxidation and reduction. Now we've talked about oxidation and reduction in terms of electron transfer. Oxidation is loss of electrons, reduction is gain of electrons. Oil rig, we looked at that in our physical chemistry unit. And that is still true whenever we use oxidation and reduction, that's always true. But when we're looking at it from an organic chemistry perspective, rather, we're not really focusing on the electron pushing, rather we're focusing on where they traditionally got the names from. It's rather if we're adding oxygen or if we're removing oxygen, or conversely, if we're removing hydrogen or adding hydrogen. What do I mean by that? Oxidation is the addition of oxygen, that's where it gets the name from, oxidation, and or the removal of hydrogen atoms from a molecule. Now, like I said just before, oil rig is always true. Oxidation is always loss of electrons. Reduction is always gain of electrons. We just look at it from a slightly different angle when we're in OChem. Now, we use this symbol bracket O bracket to represent oxidizing agent and simplify the equation. We're going to look at all these types of things that we can use to oxidize, but when we're in a chemical, when we're writing an organic reaction, we can just simply say that we got some sort of source of oxygen by doing that, because the mechanisms of these can be quite intricate and not stuff that we have to look at right now. For example, the partial oxidation of ethanol to ethanol. So we've got ethanol, we use our oxidizing agent, we symbolize it with the brackets O, and we oxidize it to another, to an aldehyde. So in this case, if we look at the reactant, which was our ethanol, and if we look at the product, which is our ethanol. Yep. And let's look at how we could define this as an oxidation. Now, we said the addition or the removal of hydrogen atoms from a molecule. If we have a look over here, we have started with 1, 2, 3, 4, 5 hydrogens plus the hydrogen on the OH. Over here, we've only got 1, 2, 3, 4. So we've got an oxidation because we're removing the hydrogen. You can also think in terms of we're adding more oxygen bonds to the carbon there. But like I said, we could just represent this by doing the O, our oxidizing agent, our source of the oxidation, by just putting it in brackets like that. And then the last one, you might be able to predict what it is. It is reduction. And the same way that reduction is the opposite of oxidation. When we look at the electron transfer, the same thing is true here. Reduction is the removal of oxygen, oxidation is the addition of oxygen. Conversely, reduction is the addition of hydrogen, whereas oxidation is the removal of hydrogen. And we use the symbol bracket H to represent a reducing agent and simplify the equation. Reduction of a ketone to an alcohol. So let's have a look at both of these products to see where we are either losing the oxygen or gaining the hydrogen. So we've got our ketone, which looks like this. Yep. And then our hydrogens, fill them in. That's already got 4 bonds, so we just got to do that there. And then we reduce that to an alcohol, which looks like this. And then add all of our hydrogens in, and straight away we can see that we have added hydrogen. We got 3, 6 hydrogens over there. We got 3, 6, 7, 8 hydrogens on that side. So we've got our reduction, reducing agent with the H in the brackets. Now we are adding 2 hydrogens in the reduction of this reaction. So we've got to make sure that we're still obeying the conservation of mass. So in this instance, we put 2 because it's saying that we need 2 molar equivalents because we're adding the 2 hydrogens. Last time we were just removing the 1 oxygen, so we just had the 1 bracket O. But if we look down here, we can see that we've got the 2 bracket H to make sure that these are balanced. Excellent, and with that we have concluded our introduction to organic chemistry. What have we done today? We've interpreted and used the following terminology associated with types of reactions: functional group, homolytic and heterolytic fission, free radical, initiation, propagation, termination, nucleophile, electrophile, addition, substitution, elimination, hydrolysis, condensation, oxidation and reduction. Equations for organic redox reactions, the symbol O and H are acceptable for oxidizing and reducing agents. Here are the tasks. Pause, work through those columns, start at the bottom, work your way up. Excellent, well done getting through that introduction to organic chem. Now, like I've been saying all through the past 3 videos now in this unit, this is just laying the foundations, and there was a huge amount of information to introduce to us. A whole bunch of new vocabulary, a whole bunch of new concepts. Now we're going to use these so much more and more, and we're going to keep consolidating that as we look at different areas of organic chemistry in a lot more detail. So just be aware of everything that we need to know, but we're going to practice a lot more in the upcoming lessons, which I will see you on very soon. Have a great one. See you later.